Hello, everyone. Welcome to the Temporal Graph Reading Group today on February 20th. Uh, we are very glad to host Andreas and Jess, who will be presenting their recent work, um, reproducibility study of explaining temporal graph models through an Explorer-Navigator framework at the TMLR and Europe's journal track. Um, and on our speakers, Andreas Berentzen began his journey in AI in 2017 and studied at the University of Amsterdam. He completed his bachelor's in 2021 and had 2.5 years as an ML consultant and developer. He then go back to university to pursue a master degree in AI, try to understand contemporary neural networks. And he presented GraphML project at ICML 2024 and UPS 2024. He is working on his thesis at the moment and exploring graph-based unsupervised anomaly detection for operational technology. And he's passionate about graph learning and looking to advance the field. We don't have too much intro on hand for you, Jess. So do you want to maybe quickly self-introduce?
Yeah, for sure. So, hi, I'm Jesse. I am I'm a master's. I am interested mostly in the field of IR currently, but I'm also looking at the crossover between IR and graph neural networks. And I started an internship recently at a IR firm called Zeta Alpha, who
Okay.
so do maintain a big documents set for AI papers.
So IR means information retrieval.
Information retrieval, yeah.
Okay, cool. Not infrared sensor or something. Okay.
No, I don't know what that is.
Okay, sounds good. So we'll pass the mic to you and start the presentation.
Cool. All right, let's do it. I'll share my screen real quick. Can everyone see my screen?
Yes, we can
Yes.
share your screen. Yeah.
Okay, perfect.
Um,
Maybe you can start it, yes.
yeah, awesome. So, hi everyone. Glad that you guys are here. So, we are briefly presenting a reproducibility study on the first of its kind, temporal graph explainer, continuous temporal graph explainer. We kind of rolled into this project by coursework for a course where we had to replicate a paper, and we continued on it, and we made a cool work out of it, and we're going to present it now. So you can go to the next slide. We did it with two teammates, but they are not here today. So what are we talking about? Temporal graph neural network explanations are hard. I don't know if you guys are familiar with the field of temporal graph explainers, or that you guys are mostly focused on other aspects of temporal graphs. But this is a paper about the most difficult case. So we're talking about temporal graphs, and they're also continuous data. So the data can shift whenever it wants to, and there can be different gaps between the time steps. Also, the graph can grow and shrink in whatever size it seems fit. So the authors of the original paper suggest a method to try to explain it. You can go to the next slide.
Okay, so I can get in. So to give an overview, this is an instance level explainer for temporal graph link prediction. Um, it really functions on top of a prediction model, and we use as baselines. These are two important temporal graph link prediction models, TGAT and TGN, which some of you might know. So this really functions on top to try to explain the link prediction that these temporal graph forecasting models make. And so what exactly does TGNM predict? It's an instance level explainer, and it predicts So it predicts the next timestamp. So we're focusing just on this one predicted event, edge event, that has been predicted by the temporal graph neural network. And so the goal is to explain this prediction. And the word explained is quite difficult to define. And so what we mean by explaining, or what the authors of this paper mean by explaining, is what we'll get into here. Okay, so we start with an initial explanatory subgraph. The full underlying graph can be absolutely gigantic. As you may know, in the social networks, a lot of evolving networks can be huge. So we start with an initial explanatory subgraph, which is governed, the size of it is governed by a hyperparameter. So we take the most recent events based on the predicted events, let's say the 50 most recent events. And we want to reduce this full initial explanatory subgraph into a final explanatory subgraph. So really a small, that we can also govern the size of this final explanatory subgraph with a hyperparameter. And what we mean by explaining, how it explains, is what we'll define later. But this is the core idea. And this is done with the Explorere-Navigator framework that is introduced in the original paper and that we have reproduced. So let's talk a little about the Explorere-Navigator framework, which is the core methodology. Good. So it consists of two parts, and together they govern the full search. The Explorer is really the broad heuristic. It decides the broader direction, and the Navigator does the actual pruning of the events themselves. So it's sort of like a high level versus low level distinction between the two. I think this will all be explained, because what we're going to do is we're going to go over a toy example. By the way, if there's any questions right now, please let me know. But otherwise, I'll continue with this toy example. So it works with rollouts. One rollout is a full pruning from the starting initial explanatory subgraph into the final explanatory subgraph, which are both governed by a hyperparameter. Of course, the larger the difference is between the start and the end, the more expensive training will be. But also the number of the higher the search space is, essentially, because there are more options of pruning. There are more. There are more. Yeah.
If I can jump in, the idea is kind of that the whole graph, the entire graph, is a perfect explanation, right? Because the whole graph, you given inputs and it gives an output, it explains why the thing happens. But the whole graph is too complex, so we're just looking at a neighborhood based on parameters, and we're trying to see if that neighborhood still accurately predicts the link being there or being not there.
Yeah, that might indeed be an important thing to say already. You're right. So the accuracy of the explanation is defined by how much it differs. So the prediction probability of event EK by the full graph GK versus the reduced subgraph. So if the prediction probability of event EK is way smaller or way larger, given the reduced subgraph, so the final explanatory subgraph, that means it's not a good explanation, right? We want to stay as close as possible to the full graph, or to the prediction probability of the full graph. Good, but we'll get into that later. So we start with a number of rollouts. This is also
just a quick question. So is it possible that under the full graph, there's multiple subgraphs that are of different sizes that will produce the same probability, the same prediction probability as the original on the full graph? So then actually there's like, does it say anything about one explanation? There's always one correct explanation, or they are guarantees to be a set of explanation that will be equally explainable, basically.
Yeah. I would say you bring up a fair point. The assumptions are that we haven't explored it, but I'm sure there would be different subgraphs that give similar accuracies. We work from the assumption that it's going to be that the current event, the current link that we're predicting, is going to be in the same neighborhoods temporally and spatially as the event that we're predicting. So we're only searching a subspace in that area, and in that area we statistically get the best subgraph often.
Based on the predicted score from the model.
Yeah.
Exactly.
Okay.
So in this whole process, the prediction model is continuously inferenced based on reduced subgraph or with reduced subgraphs to see what the prediction probability is of event EK. And based on the fluctuation of that, or the difference of the prediction probability with the reduced subgraph in comparison to the full subgraph, we change or we decide which path to go, which I'll explain now. So it's entirely possible that there are multiple optimal subgraphs. Yeah. Okay,
Yeah, thanks.
So the first step, so it's a Monte Carlo tree search, so it's a depth first search, and the navigator decides which edge will be removed. So this navigator is just a fancy similarity function, and it functions on the premise that the edge that has the lowest similarity output with our predicted edge will be pruned. That is the core assumption. And this is our very first rollout. So this means that no path has been traversed yet. And so the navigator simply decides which edges will be pruned until we reach a leaf node. So important to say here is that nodes right now mean nodes in the Monte Carlo tree search, which should not be confused with nodes in the graph that we're pruning. So right now we have reached the number of events in the final explanatory subgraph that satisfies our hyperparameter that governs how large our final explanatory subgraph should be. And then the cumulative or the reward for this final explanatory subgraph is calculated based on the cross entropy loss. And this cross entropy loss, it essentially calculates, okay, what is the probability for this event happening with the initial explanatory subgraph versus the new or the final explanatory subgraph that we just found for both the option of it existing and not existing, which is native to cross entropy loss. And then we calculate the cumulative reward, and we set a number 1, which is the number of times that this path has been traversed. And we backtrack this all the way to the initial explanatory subgraph. And this is what we call a rollout. So it's like one traversal into the big search space of graph prunings, essentially. And then we go to the second rollout, and because it's breadth first search, we choose a new path. We always choose the path that has not been explored. And again, we calculate the reward. This time, the reward was not as high as in the previous. So now we get to the third rollout. And now the question is, okay, so we assume that we've traversed all paths. And this is the only option. The only option are traversed paths, essentially, because that will happen at some point. And this is where the Explorer comes in. So now we have to choose between two prunings. Like it's at the start of the search. And we have to decide which path to go into, and both have been traversed already. And this is where the exploration and this is where we have to balance between exploitation and exploration. So this is what this node selection does. The exploitation term simply selects the path that has the highest cumulative reward, and this is balanced with an exploration term which incentivizes for traversing paths that have not been traversed that often. And this can be balanced with a hyperparameter, lambda. And so in this case, we simply calculated they both have been traversed once, so the exploration term is identical for the two options, and option 1 has the highest cumulative reward, so we will choose that option. And now we reach the point where we can do a new pruning, which happens because we always choose the unexplored path. And now we get to the leaf node, and this, because we've chosen 3 rollouts, the whole method ends here, and we choose the first back propagation. And now, because we've reached 3 rollouts, the final explanatory subgraph is simply the final subgraph that has the highest reward. So of which so that has the lowest cross entropy. So this is an overview of the method. And let's get into the evaluation metrics. By the way, if there's any questions about the functioning, you can ask it now or you can ask it later. So I think one thing to take home is that the core, this is not a deep learning approach. This is really an approach that tackles the core issue of, okay, we have a prediction model, and we're going to use this prediction model to find a smaller subgraph that retains most of the information of the entire subgraph for this specific prediction event.
And I would also like to add briefly that we should point out that this is it's a greedy search method. We remove one event at a time. So theoretically, it could be that there's interactive effects between events that actually lead to different explanatory subgraphs if we had pruned 2 events at a time, for example.
Yeah. So this method prunes 1 edge at a time, but of course, the effects. Yeah, exactly what Jesse said. This is kind of an assumption of the method itself. Yeah, it's very important to also understand. It's a shortcoming of this method. Yeah. You can take it away.
All right. So evaluation metrics. We are mostly focused on a metric that is a derivative from an AUC curve, but we call it a AUFSC curve, which is the area under the fidelity sparsity curve. So fidelity and sparsity, Andreas has already mentioned these aspects, but what we're trying to do is we're trying to have as small as possible subgraph, explanatory subgraph, but we want it to be as accurate as possible. So as close as possible. No, actually that's incorrect. We want it to be have the highest accuracy possible. So, for example, when the initial entire graph predicts an event with, when the initial subgraph predicts an event with 0.7 accuracy, we are actually going for a prediction of 1. So we're pruning towards 1. And we're balancing this out with the sparsity. So if we need a bigger subgraph to get a higher accuracy, it's going to be less sparse. Any questions about these metrics? No, perfect. We can go on. We just extended with another data set that we thought was relevant. And we explored the hyperparameters. So let's get into the replication. We're not going to show too many tables because that's not going to really be expressive. I'll show some graphs later. But what we actually found with our replication is that the method is not that stable. It has varying results, and the main finding is that a baseline method, which is called p-bone, which was arbitrarily taking away nodes from the graph, actually performs quite well, sometimes even better than this whole TGNN explainer, while the TGNN explainer is orders of magnitude, I think 2 orders of magnitude slower. I think it's 0.323 seconds. Yeah. TGNN explainer on average performed best though, but not as well as the original study reported. And in general, this method is very expensive. So the whole exploration of 500, we do 500 rollouts. We found that those have the best result, but it takes a long time. Nothing much more to say about that. Except that we calculated that you could drive a car from the Netherlands to Paris back and forth with the cost that we spend reproducing the study.
Yeah, so
yeah,
that's good. Yeah, what I wanted to add is that the more you prune, so the larger the difference between the size of your initial explanatory subgraph and the final explanatory subgraph, that will really dictate how difficult the problem is. And the amount of rollouts that you choose will dictate how much you decide to explore that space. And yeah, it can get really expensive if you have a high number of rollouts. So that's definitely something to consider. References for now, I think we can go on. I don't know how this slide got in.
Yeah, I'll just if you can go next.
Yeah, this is
yeah, so these are results on the data sets we used. So notable are the p-bone explainer, done in orange, and the subgraph X, which is our method, and is visible on the simulated data sets. We had 2 simulation data sets that were very small, easy to understand. The model performed best, but on a realistic setting, it actually performed worse on the TGN. Also, another relevant finding is the authors also claim that the method is model agnostic, so that the underlying model doesn't change the outcome, and our results beg to differ. So our results show that the underlying model actually heavily influences the accuracy of the method, but mostly the variability. So some data sets perform a lot more consistent with the TGAT underlying model versus the TGN. The TGN was a lot more variable. Is there anything else I should mention here? I don't think so. Things I have.
Are you sure the variance on TGN is because the explainer, not because the TGN itself? The variance is high.
Yeah, that's a very that's completely possible. So this model, of course, is influenced by the underlying model. So
when you are repeating trials, do you also retrain a TGN for each seed, or do you use the same TGN pre-train?
Andreas?
We use the same pre-trained TGN.
Okay, I see.
Yeah.
Because the TGN-based model also can have high variance sometimes.
Yeah, I do recall though that the models had a very high scores on accuracy, like the underlying models on all data sets.
True.
But that's with random negatives, right? So you like anything can do pretty well on that AUC. Like most models do, like pretty well on that. But yeah, like the variance, what I see is from TGB side. You can see more variance there. But yeah, and I think the terminology model agnostic doesn't mean that the model performance doesn't depend on the baseline model. It just means that you can apply this to any model. It's not specifically designed for a single model. If that makes sense.
I conflated the terms, but they do in the original paper they do claim it is irrespective of the underlying model. the accuracy of their model.
I see. Yeah, but the finding is very interesting. And it kind of makes sense because if you're using the random sampling with the Monte Carlo and there's a lot of like variance in that, right?
Mm-hmm.
Yeah, so they try to alleviate that variance by using the Navigator model, but yeah, to no avail, it seems.
Yeah, it's like it's two models on top of each other. So the randomness in TGN, for instance, it compiles on top of the randomness that this model has. So to like robustly evaluate it, you should have multiple trainings of TGN, and then
Yeah.
all use and then also have multiple
So
rollouts for
like
each data
9
set.
trials, like 3 for each TGN based model pre-trained weight. So then
Yeah,
you average over that and probably you get something more statistically significant because of
yeah.
all
I
the
wonder where we could
randomness. Yeah.
have, I wonder where we could have driven on that money.
Yeah, true. No, but if I would do this again, I would be very uh, careful with what data sets I select. Um, I would maybe go for a smaller data set, and I would do it like you said, Andy, where you have multiple trainings of the underlying model, multiple trainings of this model, and then you would just do a smaller amount of pruning. Like you would go
Hmm.
from 10 to 5 maybe. And in that way it's less expensive, but you can have that robust experimental ground. So
Hmm.
that's what I maybe would do different. But we were all, of course, focused on reproducing the original results, which were on like very large data sets and
Hmm.
with high rollout numbers. And yeah,
Yep.
but that's definitely a point of improvement for.
I would also say that's basically our presentation. Like, there's a couple of slides where we're just talking about things that were relevant for us. I'm not sure we need to pause on these, Andreas. I think we can just share the slides.
Let me see. Yeah, I think this would still be cool to go
Yeah.
over. So we
Yeah, I
also
think
thought
this is
about a bit of a.
interesting.
Okay, let's talk about it. Do you want to talk about it, Andreas?
So the way that the Explorere-Navigator is trained right now is based on categorical cross entropy of the um, of the prediction with the original graph versus the prediction with the reduced graph size. Which a different loss function could be interesting, where we're just trying to maximize, or yeah, we're trying to find the initial explanatory subgraph that maximizes the correct. Oh no, I think that it's exactly what happened. I'm sorry, that's a confusion from me. So we're trying to find an explanatory subgraph that potentially explains or no, that achieves higher accuracy on the data than the original explanatory subgraph. So if the event has been accurately classified, so it is actually the next event that will happen, and with the original explanatory subgraph, the probability was 0.8. With our final explanatory subgraph, we're incentivizing the model to output 0.9 or as close as 1 as possible. But this is done with a categorical cross entropy, so we thought maybe a different one or a different loss function could lead to different results.
So we also found that this current model actually only works on a very specific type of data. So it had to be, well, of course, continuous, event-based, unidirectional, and it allowed for multiple edges between nodes. I think it would be valuable to explore this method also for different types of data structures. And We would like to appreciate this study for being the first of its kind. So this is actually the first explainability method, instance level explainability method for continuous temporal graphs. Since then, there has been one more paper, as far as I know, in this field. I didn't put it in the slides, but I can share it here.
The temporal motif one, right?
Yes, exactly.
So I think that one is a bit more easier to understand to me, like more intuitive at first. I think this one is more heuristic-like approach on that. And also just going back to a little bit, so which data sets to test on? Can you remind me which data set, the real data set?
That's a yeah. I don't know if we have a slide on it, but I can definitely
No.
tell you. So there are two synthetic data sets, two real ones, and then we added another real one. So
Okay.
two synthetic data sets, they're synthetic and they only have 4 or 5 nodes. And there's continuous interaction between these 5 nodes
Okay.
based on a tick process. I think it's like a physics process to simulate interactions between particles. But it's essentially a toy data set. Then we have Reddit, which is a bipartite temporal graph of users interacting with online content, like, well, Reddit posts. And then there's Wiki. Yeah, sorry.
Yeah, same goes for Wikipedia. It's also users, and it's also bipartite users and pages. They're editing pages. And we added the MOOC dataset, which is a school education network, again, of students doing education, doing games or something.
Yeah.
So
and
which data set was the best performing one for the model? Do you recall? Because I'm thinking there might be some pattern to the data set. Like, for example, how much percentage of the edges are repeating, or what's the amount of new information that appears in data sets. So these all varies significantly across data sets. So could be part of the explanation why it works well on some while it doesn't work well on others.
One pattern that was definitely there is that it was much better on this simulated data sets, which is quite logical since they're simpler. I think. So what I can say is that we chose the MOOC dataset based on the features that it has. So Reddit and Wikipedia both have, I think, 160 features per event. And MOOC dataset only has 4 or 5, which means that the navigator, it functions differently, or it has a different effect on the navigator than with Reddit and Wiki. Would have been really nice to add. If you want, I can take a look at the paper. But there are also, so if you want to know this, it's definitely in our paper. There's also differences in average degree and connectivity in these Reddit and Wikipedia and MOOC dataset. We also analyzed that in our paper, and we try to see if there's a pattern between explainer performance and these dataset characteristics.
Cool. Nice. Yeah, so that's mostly my questions. Do you want to go back to the slides of future directions, and we can, we can also take questions from the audience, of course.
Let's finish the slides. So one more slide after this is just a brief summary of what we did. And I think we can also just end it here. So we'd love to take some questions if people have any.
Yeah, so thanks for the great talk. Do you have some questions, Julia?
And maybe just on the runtime. So you said, I think you kind of said that it was a bit like long to run and so on. Do you have some kind of numbers? For example, if you train TGN and then on top you have the explainer, how much longer does it take to have the explainer on top?
How long did it take to run one data set? I'm sorry, it's like a year plus ago.
This is more than a year ago.
Yeah.
Sorry, it's not a problem if you don't
I
remember.
think I think
A
some
total
running
number,
training
yeah.
jobs were like 16 hours, but I think it's more
No,
dependent
it's
on
more.
the
It's more.
yeah, but it's very dependent on the data set size.
Yeah, so the average here we have it. Average time was 4 hours for the underlying model and 26 hours for each explainer on top.
Okay, so it's significantly longer than the underlying models.
Yeah.
I mean, that's an important takeaway, I guess.
Yeah.
Okay, thanks.
Yeah, it's a very slow method, but I must say it was also just not optimized well. Like I think it could be a lot quicker if we improved GPU usage.
Yeah, so the original paper was like, these are our results. We have a significant improvement, and this means that it's 50% better than other explainability baselines. And what we found basically is that there's more randomness to it. Although it seems to perform well, on some data sets it is not the best, and it can be beaten by a simple like perturb1 explainability, which doesn't have all the heuristic calculations that this method has. So I wish that this would be clarifying and be like, okay, we've added something to the conclusion to make them stronger from the original paper, but it's actually more of making things more nuanced.
Yeah, and that's taken together with the computational cost is definitely something to take into account.
I think that's an important insight for sure. And then you also said in one of your points that it would be potentially useful to come up with more baselines, which are potentially less expensive and maybe as good, right?
So the point that we kind of took away, I think our conclusion at the end of the study was that apparently such a simple method as perturb1 already achieves quite well. Maybe this whole structure that they thought of is just too much computational overhead compared to the results, and maybe they should explore different methods further instead of just keeping them as a baseline.
Yeah. Okay. Yeah, it makes sense. And we also have a question in the chat. What would be the idea to implement it at graph level?
Yeah, that's not
the idea to implement at graph level.
That was one of our teammates that had a big focus on that. I'm not sure if we fully know what she intended by that.
You mean at graph level instead of temporal graphs?
No, instead of instance level.
Oh.
So I guess more like subgraph level, which is like the temporal motif paper, which is like a small subgraph.
Mm-hmm.
But you still want your explanation to be local though, because if it's too big, well, like the entire graph, then there's nothing that you can zoom in to see the effect of.
Mm-hmm.
Do you know anything about the explainer on temporal knowledge graphs, Julia?
There's one which also does some subgraph kind of finding. It's a bit complicated and it's also super slow. It's called Explorere. But it's a similar kind of thing. So for predicting a link, what you do is you're trying to find a subgraph that somewhat explains the prediction on this link. It's quite a while ago that I read this paper. I can copy it in the chat.
Interesting, but
it's from 2020. I put it in that chat.
Yeah.
Thank you.
Yeah, thanks, Julia. Yeah, so we can. There's not too much questions from my end. I just have a final comment. I feel like I'm not the expert on explainability, but I think the task itself is basically a tensor sub-indexing operation. So you are optimizing some objective to find the smallest set of tensor that will give you the same cost, basically, the same predictive probability. Because if you can look at temporal graph as a tensor, right, you have the graph as a dimension. So you have n times n, which is the edge index. You have t, which is the timestamps. And you are basically slicing this tensor and you go into a small explainable set. So that's all these methods are doing. They are trying to cut down on the size using different heuristic to reduce in some sort of learnable way. Right.
Yeah.
But
So
that's
while
what
focusing on achieving the same probability value.
with in relation to some objective function. But we know that, like, for example, finding subgraphs, like trying all kind of subgraphs in graph is like NP hard, right? So so that kind of boils down to the difficulty with that.
I like that conceptualization. I hadn't thought of it like that, actually. That it's a string of graphs stuck together.
So all the MC stuff you are doing is just you are trying to narrow down on this tensor, and then you are seeing, okay, now I have a new tensor index. How good is this to the objective? And then if it's not bad, then I keep it. If it's bad, then I try to go a different way to reduce the size. Right? But of course, this space of all the possible index is very large. So you're searching over extensively large space. But the hope is that there are some pattern in the model such that you can find a low dimensional manifold where you can zoom into the index, the correct index in polynomial time, say. But anyways,
that's a difficult question. Or and now they use that heuristic by previous iterations, and then using the reward of one rollout and essentially assigning that value to each other slice or each other rollout or each value in that rollout. But ideally, you want to look inside the TGN or TGAT model and see if inside there might be some indications of what reduction is the best for preserving that probability value.
I mean, the model internally are putting more emphasis on certain paths than other paths. I mean, that's why this would work to begin with, right? If the model internally just randomly aggregating information from all past neighbors, then there's nothing you can learn here. Okay. So thanks for the discussion and thanks for the presentation. So we can wrap up the talk for today. So again, very interesting paper. And then hopefully, if you have a chance to follow up on this, I think this is a very interesting direction that still relatively new and not much worked on. So definitely good to have your paper and have good code to go with that and so on. So yeah.
Well, thank you so much for the invitation.
Yeah. Thank you so much for the invitation. And thank you, Julia.
Thank you for coming. Thank you for presenting.
Yeah, no problem. And
by the way, we really cleaned up the code base. So we have a new code base for this paper, and it was a mess and it was a struggle, but we cleaned it up and now it's much more runnable. So if you want to try it out yourself, then it's also in our paper, the code. So
that's quite a useful contribution.
If you want. That's the biggest round contribution probably.
Yeah. Right, awesome. Right. Thank you guys.
See you guys. Thank you.
Yeah.
Bye-bye.
See you.
Bye.
Bye.